Okay, let's get going. So, monitoring and decision making, we are finally out of the ecology sort of overview of all of the background information that lead us into IPM, and now we're getting into more of the actual workings of IPM, how we do it, and some of the theory around it. So quick announcements before we get going. A reminder that next week is the World Ag Expo on Tuesday, Wednesday, and Thursday. So there won't be any lecture or lab on Tuesday, and there won't be lab on Tuesday or Thursday. So basically you can take that time to go to the World Ag Expo, or you could take that time to not go to the World Ag Expo. That's your business, whichever one you choose to do. However, if you do go to the World Ag Expo, there is an extra credit assignment that you can perform. It's worth 10 points. Essentially, you go, you visit some booths that are related to pest control, and you do a short write-up, just sort of explaining how you could integrate those different techniques into an IPM plan. Along with the paper, you'll have to turn in either a picture of yourself at the World Ag Expo or a copy of the ticket to get in. So, you know, don't. Yes?
You know I'm going to ask a question.
Of course.
Why
should I expect it?
Is there a possibility for extra credit for those who can't or are not going?
Oh! There might be a possibility. We'll see. We'll address that more specifically another time.
The reading thing, is there going to be one for Tuesday?
No. Yeah, so since we don't have a actual lecture on Tuesday, there's no reading due on Tuesday. So I believe as the syllabus has it right now, we do have one for Tuesday because I was initially planning on canceling the Thursday lecture instead. So we'll be doing everything we're going to do on Tuesday on Thursday. I'll put up an announcement to that effect just as a reminder. So speak of the quiz, this was it. As far as question 1 was concerned, that we asked you about sampling a vineyard for mealybug crawlers, where the particular protocol was that you looked at individual spurs under the bark to count the mealybugs. And so we asked what the spur was. The new spur is which of these? The unit, the university, or none of the above? Right, it is the unit. So generally that one was a little easy. Most people got that it was a sampling unit. I was pleased that nobody answered sampling university. That would have been embarrassing. And this second one, we noticed that when you are sampling and you take the average number, you find that the average number of mealybugs per spur is fairly representative of the population as a whole. But you find that the individual counts can kind of be spread all over the place, that they don't all hit really close. You have to take the average to get that close value. So this would suggest that our test is which of these? Low accuracy, low precision. I'm not going to read all those out loud. It is C, yes. That it has high accuracy and low precision. So accuracy, in terms of sampling, is our measure of how close we are to the true value, the true population in this case. Whereas precision is our measure of how similar our individual samplings are, right? We'll go over that again in the lecture, but that's the basic differentiation. So because when we took the average, we were close to the true value, it's highly accurate, but because the individual counts were all over the place, they were a little bit more spread out, so that would be low precision. All right, so monitoring. Monitoring, broadly defined, and monitoring is very broadly defined according to the IPM textbook, and generally is broad, is any procedure used to observe, measure, and record over time the activities, growth, development, and abundance of organisms or the factors that affect them. So, some things I'd like to point out about this definition before we move on is that first, notice that monitoring has multiple steps, that it's not just good enough to basically go out and look at a field. We actually need to be doing several things. The first of which is we have to observe, right? So this is the part of monitoring that seems the most obvious. We go out, we look, we see what is going on in the natural system. But it's not just good enough to observe. We can't just go out and say, oh, there's grasshoppers, or oh, there's nematodes, or whatever. After that, we have to actually measure how many of them there are, right? Because it's not good enough to come back and just tell the grower, I saw some, nematode damage, or I saw some grasshoppers or something. They're going to want to know, is it a problem, or is it, not? And when do I need to worry? And then finally, you record. So monitoring isn't a one-off sort of thing. You just don't go out and monitor once. You monitor, you record it, and you keep that record. Because by keeping the record, we can take a look at how those populations change, right? We can basically estimate whether populations are going up, if populations are going down, they're kind of staying the same. We can estimate trends over time. And without keeping those records, without moving forward in time, we can't do that. We're basically stuck with one-off little time points. And finally, last thing I'd like to point out is also that monitoring is not limited to looking at actual organisms, counting actual pests, actual biocontrol. There's also monitoring includes things like looking at, where is it here specifically? Well, basically, looking at anything that affects the activity's growth or development. So we may be looking at the organism, but we may also be looking at climatic data. We may be looking at temperatures. Monitoring can cover any variety of things. And so essentially, common activities that fall under monitoring would include things like looking at the actual population levels. That'd be the most sort of obvious form of monitoring. But it can include looking at stages of development in the field, whether it's the crop or the pest, to get an idea of when either one of them is becoming susceptible or damaging. Looking at, as I mentioned before, things that affect the pest indirectly, like weather and crop development. And also monitoring is something we do even after we have decided to control the pest, because we want to know whether our control practices worked. We want to know if we maybe had some negative effect on our natural enemies, those sorts of ideas. And then ideally, over the long run, what all of this monitoring does, by monitoring the same field over multiple growing seasons, it gives us a really nice history of the pests we have there. And we can take that history and we can basically streamline our future efforts so that we're not wasting time on things we don't see, and we're also really targeting those pests that are the biggest problems consistently. So monitoring is just something that you kind of do over the entirety of your career in a particular system. So why monitor? Well, I think I kind of outlined a whole lot of that. But if we go back to what we discussed in the first couple of lectures, the idea that IPM is a decision-making process with these various steps that we're moving through, monitoring really is sort of the key to that decision-making process, right? It's step 2 after we've identified a pest, and it really determines how we move into the assessment and finally whether we do need to implement or not. Excuse me. So ultimately, in IPM, the major function that monitoring provides is this number 1 up here, that it's basically a tool to reduce risk. It reduces the chance that we basically apply a control we don't need to, and it also reduces the chances that we miss a control application that we do need. And so, oh gosh, there's a whole bunch of those. Look at that. So ultimately, it's a major tool also for helping to identify those patterns, so we make sure we are making the correct decision. Allows us to make justified pest management decisions to growers. So if you go to a grower and you want them to apply some sort of expensive pesticide, or you want them to replant next year using a different variety of the crop that's more resistant, it's going to be a lot more convincing if you can walk in with a nice piece of monitoring data that says you have this problem. This problem is causing you this much yield loss. And so having that nice justification makes your job easier. And also, if someone comes back on you, and if you're a PCA and you're getting sued because someone lost money or they feel like they got treated when they didn't need to, you can always say, well, here are the numbers. I've been keeping an eye on this. Also, it's backup information for estimating treatment effectiveness. So you'll have numbers before and after a treatment, so you'll know whether you're starting to develop resistance problems or if you have resurgence issues. And finally, it ultimately saves money, and it protects the environment, which is great. So ultimately, as a PCA, or as anyone who's doing IPM, monitoring data as a PCA, you should be able to go into a field and estimate the density of the pest population, evaluate the potential impacts that this population will have on the crop, and then determine whether or not this control is needed. So ultimately, monitoring kind of covers steps 2 and 3. They only put monitoring as step 2. I'm going to lump in assessment as well because I don't want to do a whole lecture on assessment. All right. So one important distinction I want to make before we move on is that monitoring and sampling are 2 distinct things from one another, right? And so I'm going to spend a fair amount of time talking about sampling. And so I just want to establish how they differ from one another. So monitoring is the total process of watching the activities, the growth, and the development of the pest organisms or other factors. So it's the total process. It's that observation, measuring, and recording over time. So it's the whole thing. Whereas sampling, on the other side, is the actual active collection of measurements from a part of the population or features of the environment. So you can think of sampling as the active process of getting those numbers that we use for monitoring. And the basic idea of sampling is that if we're out monitoring a field, right? And let's say we're interested in nematode populations. We want to know how many of them there are. Well, clearly, in a large field that's several acres across, we can't just go through and count, every single stinking nematode that's in the entire thing, because the numbers would be huge. And plus, to sample nematodes effectively, you'd have to basically turn over all the soil and basically sort of filter it all out, get all your nematodes through all of those little meshes. It would be a huge pain. So sampling is a way to get around that. We basically say, well, instead of getting a true count of the entire population, let's just do little soil samples from a couple spots in the field, say like 5 of them. We'll count the nematodes there, and we'll use that estimate from those little samples to get an idea of what the total population looks like. And so basically, measurements of a subset allow us to extrapolate patterns for the whole population. And ultimately, we would really like these measurements, because we're basically relying on these samples being correct, we want these samples to be accurate and very precise. So ultimately, sampling is the backbone of monitoring. When you're out monitoring, when you're talking about monitoring, mostly what you're doing is you're sampling, you're collecting data, but it should be noted that there are certain things that aren't necessarily sampling. We do have a few things that are real-time, like climactic data. You can get climactic data that's continuous across the entire day, maintaining sort of landscape maps of where pests and weeds show up. That's not necessarily sampling. They kind of fall out into different patterns. My thinking is that the more big data that agriculture gets, the more people are reliant on things like drones, and the better those technologies get, we might become less reliant on sampling overall, or at least the way we sample will change, because we might have a better ability to process large data sets. But for the time being, sampling is not going anywhere, and it's not going to go anywhere for people working in smaller crops that don't command the amount of commodity dollars that large crops do. Oh?
Yeah, there's a lot of information on that page.
I'm sorry, did I delete a whole lot off the slide?
Did you change your PowerPoints after you post them?
I sometimes do.
Because I take notes over the weekend.
I
film
know,
it,
I'm
'cause I don't
sorry.
forget, and
I
don't
sometimes
have
do,
things.
'cause I-
Gosh.
I write them, then I edit them down,
And it
and then
gets
I get
all-
up in the morning, like today, and I review it before I come in, and I'm kind of like, I don't like that slide. We'll check that one out.
You're new.
I'm working here. I'm working here. This is the second time I've taught this class. Yeah, we're working through it. That's right. It's a process. 3-4 years down the road, it's going to be really nailed down hard, but you are all a part of the grand process. I appreciate that. Guinea pigs. There you go. I think it's interesting that guinea pig has become established as sort of the metaphor for what test organisms are. I don't know any labs that use guinea pigs.
Nope.
But it'd be like a lab rat or a mouse or a Drosophilid fly would be more accurate. Anyway, that'll be on the test. Okay. No, still?
I told you there's a lot there.
I'm sorry, there is a lot there. To be clear, I would say focus on this top, ignore this bottom stuff.
Okay.
I'm not going to test you on that. That's more of an aside. So as long as you have the definition of monitoring sampling, and you can basically tell the difference between the two, that's the major thing that I'm trying to get across on this slide. All right. So within sampling, let's talk about sampling for a little bit. We oftentimes make a distinction between sort of the units that we sample within. And there are two important things to distinguish between and to understand about sampling in terms of space. One of which being the sampling universe, and the other one being the sampling unit. So the sampling universe is going to be the boundaries of the area for which a pest management decision is being made. This is sometimes referred to as well as a block, but the basic idea is that if you've got a field that you're monitoring, if you're planning on treating all the pests in that block as one single population, so if you decide to make a control application, you're going to apply it to the entire field, then you would consider that entire field to be the sampling universe. So generally, a sampling universe is going to be one consistent habitat type. And here in the Central Valley, the nice thing is universes are oftentimes easy to tell because they're great, big, huge, square, rectangular fields where you have all the same crop planted with all the same irrigation and all the same varieties. So it can be relatively easy to define a sampling universe because it's big, flat, the same shape, all the same stuff. You expect the pests to all behave the same way. However, if within one of those big rectangles, for whatever reason, you have any sort of factor that you expect is going to make the pests behave differently, you need to take that into account when you're sampling. For example, let's say, like down here in the corner of the screen, you've got a citrus block that you're monitoring. And over here in green, you've got the majority of the field planted as navel oranges. But up here in the blue, you've got a small patch of grapefruits. So if you were going through and you were monitoring these, for a lot of pests, the monitoring it wouldn't be any different. You could treat this as if it's one big sampling universe, because a lot of the insects that sort of affect these crops are going to be very similar. The thrips, for example, are going to behave similarly between these two types of citrus. However, there are certain pests in which you would get a very different reaction between navels and grapefruits. For example, the citrus peel miner. Navel oranges are basically immune to its effect. So if you were going through and you're seeing a lot of citrus peel miners on your cards when you're monitoring, you're looking at it, it's like, we're not worried about that in these navels. If you're treating based off the average of the entire field, you may cause a lot of damage in your grapefruit, which is susceptible to this pest, just because you're not treating them separately. You're not being mindful of the differences between those blocks. So oftentimes, it's just recommended that if you see any situation in which conditions should cause differences in pest populations, you should treat those two sections differently. So you might want to subdivide into smaller universes, depending on the pest.
For that though, wouldn't you have to spray the whole thing for the peel miners because they would just being inside the block, they just hop over? Or?
Depends. So peel miners...
Like if they're just next to each other on rows or whatever?
So the peel miners shouldn't even really be able to set up shop in the navel oranges.
Oh, they won't?
I don't believe so. I think it's a matter of skin, of cuticle thickness, that they can't even get under there. And so it's not a case where you're going to have a whole bunch of peel miners in the navels flying into the grapefruits. It's more that you would have basically leaf miners flying through the system, and some of them will settle down to the grapefruits and others will pass through because they don't find a suitable host. At least that's my interpretation, my basic understanding. So yeah, as you can see, there's lots of reasons why you may want to set up different universes, whether it's based on the planting dates, the varieties, the soil types. But let's say, though, there's some alternatives as well, things that might cause differences in pest distributions that have nothing to do with what's inside the block. So, for example, let's say you've got an almond orchard, and then right next door to it, you've got, let's say these are almonds, and over here you've got a great big field of pomegranates. Does anybody know what bug really likes to hang out in pomegranates? Right, yeah, you got tons of leaf-footed bugs over here, right? And so leaf-footed bugs really enjoy moving from pomegranate over into almonds as well. And so it might be in your best interest to put more sampling effort for leaf-footed bugs up on that side of the field, where you expect them to be coming in at greater densities, than it would be over here. So you might want to consider this field as two separate sampling universes, just based on the location. Similarly, in crops, you might want to consider sampling more heavily on edges, where migrants are likely to come in, or if you're by dusty roads, where spider mites are likely to crop up. Those sorts of things. All right, so let's say for our dormant sanitation lab, how would we define the sampling universe in this setting?
How would you define it?
How would you spell out so where would you draw your sampling universe for this?
For the entire field.
For the entire field? So for the soft and the hard shells?
No, you
Divide it.
orchard rows.
For monitoring some pests that have similar effects, then why not do the whole field?
But we're testing different
We have two different varieties, and
Oh, we're getting all sorts of different stuff.
yeah, the navel orangeworm is supposed to infest the soft shell more frequently than the hard shell.
So I think this
So you may wanna-
I think this is a really good point, that I could see arguments for either side. So on one hand, you're right, there are two different varieties. We've got soft shells and we've got hard shells. And research suggests that navel orangeworms would target the two sides differently. But are we exclusively scouting for navel orangeworms?
No, I think also when you start talking about universe, you need to decide what pests you're going to be looking for.
Right, exactly. We're looking for different pests. So maybe we would expect to see a difference between hard and soft shell for navel orangeworm, but we might expect exactly San Jose scale to be the same across blocks. Alternatively, you all went out and counted mummy nuts, and I don't think very many groups found significant differences between the two blocks as far as mummies were concerned. And in past labs where we've broken open nuts and we've looked at the infestations, we've not found significant differences between infestation rates in these blocks. So you might even say, maybe when you first come out here, you see these varieties and you say, let's treat them separately just to be safe. And over the years, as you build up that monitoring record, you start looking at it and saying, I'm wasting a lot of time looking at these two different blocks as separate. Maybe we need to change things up, and we'll consider this one big sampling universe, right? So sampling universes exactly are nuanced. They're not always going to be the same. You can switch them up based off what you find in the field, and you're going to switch them up based on what it is you're looking for. So, exactly. Again, lots of information. That's why you're all getting degrees and you have to take the test. You're expected to know a lot of this stuff. Okay, so on the flip side, we've got the sampling universe, which is sort of the biggest it goes, right? Sampling universe is the total area that you're treating as a single sort of pest population. And then we've got the sampling unit, which is the smallest unit that's sampled within that sampling universe. Sampling units are a little bit tricky. So, excuse me. Right. So essentially an object that has been sampled or collected from a larger population. So one thing I find a little bit tricky with a sampling unit and explaining it is that if we were to go out and to sample, well, I'll just ruin the unit aspect for that second question on the board. So let's say we're out there and we're sampling those spurs like we did in the almonds. So what would you guess is the sampling unit in a spur analysis?
Each spur.
Okay, so I'm hearing each spur.
No, the total of the spurs collected.
The total of the spurs, trees that you're taking them from.
It's the
All right.
object collected.
It is the object collected, right? So in this case, it is the spur. So there you go. Very well done. Sometimes what the general trend is to think of the sampling unit as the particular pest that you're looking to count, right? So you might say the unit is the individual San Jose scale. But that's not really the way we do it. We're thinking about the thing that we are actually physically collecting. So in the case of the spurs, the smallest unit is the actual spur we get. If we're out sweeping alfalfa for alfalfa weevils, the smallest unit is the sweep, the individual swing of the net, those sorts of things. Because we are actually counting the pest that's on that spur, the pests that are in that net. If we're doing nematodes, we're counting the number of nematodes in the gram of soil. But we're not actually collecting individual nematodes. We're not collecting individual aphids. We're collecting sweeps. We're collecting grams of soil. We are collecting individual spurs. So you can think of it as like aphids per sweep, nematodes per soil sample, or SJS per spur, and the sampling unit is going to be the per part. It's going to be the sweep, it's going to be the soil sample, it's going to be the spur. It is the way that we collect the actual organism. Does that make sense? So it's not the actual organism itself, but it is the way in which we do the sample is the sampling unit. So defining your sampling unit can be very important in the sense that sometimes if you do a bad job defining your sampling unit, you may be sampling in such a way that you are missing pests or you are actually maybe collecting more pests than are actually there. So for example, the way they recommend you monitor for, I believe it's the tomato fruit worm, is you're supposed to look for eggs on the leaf that is most directly underneath the bundle of flowers, essentially, the inflorescence on the plant, because that tends to be the place where they lay the most eggs. So if you end up looking at the second or third leaf underneath it, you may be looking at leaves where the caterpillar just naturally doesn't lay eggs, and you may way underestimate it. So making sure that you are using the exact right unit can give you hugely different numbers. And so there are some trade-offs with sampling units, which is essentially that you want to have a sampling unit and you want to sample enough units that you get a good assessment of the population, right? So if you're out there counting spurs, you want to make sure you count enough spurs so that a single high population on a spur or a handful of low counts aren't going to skew your entire count. You want to have enough counts so you get an accurate count. But at the same time, you don't want to be out there all day sampling. You don't want to sample huge amounts. For example, you don't want to set your unit as looking at all the San Jose scales on an entire almond tree, because it would take you stinking forever to count all the San Jose scales. Whereas having a spur is a nice, easy thing to measure because it's about this big, and you can take it back to the lab and look under the microscope. So generally, the trend we see is that the sampling unit is oftentimes going to be specific to a pest species, and in some cases, it may even be specific to a sampling universe, depending on the conditions of that sampling universe. All right. So here are just some examples of various sampling units. So again, you'll notice that they tend to be the things that we are actually collecting. So the number of sweeps for lygus bug. For aphids, it's the number of honeydew dots on a water-sensitive card, the number of citrus cutworms in new growth flushes. So the unit would be the growth flush, the card, the sweep. All right. So, I think this is the last thing I want to touch on in sampling specifically, but the other ideal is that we want to make sure that how we are sampling is both accurate and precise, as we mentioned earlier during the quiz, right? And as I mentioned then, accuracy is really a measure of how close a sample is to the reality. So essentially, how well does the sample actually represent the population as a whole? Is it close, or are we under or overestimating it? Precision, on the other hand, is like standard deviation. It's the amount of variability you have between your samples. So how close are the measurements to one another? So if we're sampling spurs, a highly precise measurement would be a bunch of spurs that are all, say, between 0 and 2 San Jose scales, whereas a less precise measurement would be a bunch of spurs where maybe a lot of them are at 0, but then you have a handful that are at like 50 or 100 San Jose scale or something, just like way off the charts, having huge amounts of variability. So a useful way to think of precision versus accuracy is to visualize it as something like target shooting. Whereas the goal in target shooting, right, is to hit the center of the target. Much like in sampling, our goal is to hit the center of the population. We want to have the most accurate estimate of the population size, which we can imagine is sort of the center of the target. So ideally, our measure is accurate and precise, as over here. We're consistently hitting the right part, so we're accurate, and we're clustering, so we are precise. On the flip side, sometimes really accurate and precise sampling methods are difficult to develop because either someone hasn't gone out to do it, or maybe it's a factor of the pest's biology that they're very sporadically dispersed, so it's hard to get a good idea of how many of them they are. Maybe it's something like a pathogen, where it lays dormant for a certain period of time, so it's hard to even tell when you have it. So it's not always possible to have accurate and precise measures. Sometimes we have to sacrifice one or the other. So if you were out sampling and you wanted to know a population density, which one would you rather get rid of, accuracy or precision?
Population density?
Precision.
Yeah, right? Why would you rather get rid of precision?
So you'd rather have some accurate data.
Right, exactly. If you get rid of precision, you're not always hitting the center of the target, but at least sometimes you are hitting the center. And if you were to take the average of all of those measures, you would still get a reasonably good estimate of the population size, or the population density. Whereas if you sacrifice accuracy, all of your hits, all of your samples are going to be very similar, but they're not going to be near the center. And since we don't know where the center is in the population, if we don't know the actual size, it's not going to help us a lot in figuring out what's going on out there, right? And then, of course, there's a worst-case scenario where you're not precise or accurate, and that can be a total train wreck. All right, so factors that affect accuracy. So things that can cause us to have tests that we're getting maybe very precise results, but they're not really close to the actual population value. So the number one factor that causes trouble with accuracy is inconsistent while sampling. So like we talked about in economic entomology, a lot of the measures that we use to estimate populations are relative, like sweep nets. When we're out sweeping something in alfalfa or in cotton, we're not counting every single alfalfa weevil that's on a plant. We're basically counting all the alfalfa weevils that fall in our net. So if you've got one scout out there sweeping for you who likes to swing the net really hard and really deep, and you've got one scout who's kind of out there like just sort of tapping the very tops of the plants, you might get very different counts between those two scouts. One guy might be way overestimating, one guy may be way underestimating, maybe one of them's accurate and one of them's not. But either way, you're not always going to get the right measurements.
When we get back to inconsistency while sampling, I know that when I was out counting those mummies on those trees, supposed to do it randomly.
Uh-huh.
Well, after counting one tree with like 500 mummy nuts on it, we started looking for trees with fewer mummy nuts.
Yeah.
So
Number
there's-
two.
No, not seven. Okay, I got it.
Yeah, no, exactly. So number 2 is not sampling randomly, which, as Daniel very convincingly pointed out, is easy to do. Ideally, all tests work because they're random. That if a test isn't necessarily, so basically, it doesn't matter so much if we're hitting the target all the time as long as we get a nice random scattering around the middle of the target that we can take the average of. But if we're skewing ourselves up towards what's easier to see, then we're going to basically pull ourselves off of that nice accurate measure that's really close to the true population value. So you see this go both ways. You do sometimes see it that people are intentionally aiming for the things that are easier to measure, such as the trees with less mummies on them, because it's a pain to count 500 mummies on a tree. One way around this is I know that a lot of people who do monitoring for things like mummy nuts, they just look at a tree and they say, it's more than 50, or greater than, 30 or something. You're supposed to have it, according to the UC, at 2 or 0.2. So if you look up and you see more than 2, it's like, does not meet sanitation standard. So you can cut out some of those biases. But on the flip side, sometimes if you've been a PCA who's in the game for a long time, maybe it's your own farm and you're used to monitoring it, you know where the hot spots are. So maybe you're over-scouting those regions where you do find pests, and so you're over-applying when really you should just be spot treating those individual hot spots. And then, as I mentioned earlier, you can have issues around inconsistency of your sampling units. So, as I mentioned, these units oftentimes are specific to species, specific to life stages. So if you are sampling the wrong unit at the wrong time, you can skew your results so they're no longer accurate. And again, another thing that's problematic when you're working with scouts who may not have the amount of background knowledge that you do on a particular system. And I already talked about the tomato fruit worm as an example. So how can we actually increase accuracy? So these are relatively straightforward, but if consistency is a problem, we need to increase consistency, right? So we should basically, if you've got scouts, you need to spend some time training them on specifically what it is that you want them to be doing. You need to basically instill in them the idea that there are certain rules and that those rules matter, so you have to follow them. Another way is that you can use multiple techniques. So if you have one technique that's maybe prone to over or underestimation, maybe have a backup technique that sort of follows up on it. So for example, if you're scouting for something like navel orangeworm, if you're using pheromone lures, but you're not really sure they're working, you can always set out egg traps as well, as sort of a backup way that if you're seeing high populations in, say, the eggs, but not in the pheromone lures, then it might be time to reconsider whether or not you actually need those sprays. Handle samples carefully. This is most important when you're talking about things that have to be analyzed in a lab. So if you're working with pathogens especially that are very sensitive, they require very specific in-plant conditions. If you're not careful, if you pluck a bunch of leaves off of a plant, throw them in a bag that you're going to send to some lab, and then you throw that leaf, that bag of leaves in the back of your hot truck and don't get back to them for a couple days, you might have fried it all to hell, and there's not going to be anything left for the lab to find. So just generally being very careful with what you collect. And then finally, accurate field notes. So the particular precision can be altered by the fact that you might be sampling under less than ideal population conditions. So maybe you're out in the rain, maybe there's a cold snap, and that's going to skew your results. So it's always useful to have field notes so that when you come back and you're like, I've got a weird looking data point, I don't know what that's about, you can maybe look at your notes and say, oh, it was really cold that day. So maybe there weren't as many pests out, and I underestimated. So generally having a notebook your notebook is your friend. It backs you up. All right, so precision. Things that affect precision. One of the key things is the distribution of the pests. So as we mentioned before, different pests have different distribution patterns. Most of them fall into the clumped, though you do get some with random, very few with nearly uniform. But if you were sampling a pest and you weren't taking into consideration how they are distributed, you could get vastly different measurements between pests, between fields. For example, if we were to say move through a field sampling just sort of in a random zigzag pattern, taking the exact same pattern and laying it over these 3 different fields, we see that we are encountering vastly different numbers of pests depending on the distribution. Also, field size and shape. So as we mentioned before, field conditions can really determine how many pests that you get in a certain area, especially things like spider mites, leafhoppers, aphids that tend to move in from weedy or dusty areas into the field. So if you've got a field that has a whole lot of edge, like if it's just sort of like some unusual shape, maybe you're dealing with a creek or some unusual land barrier. This is more of a problem in the Midwest where you've got a lot more land features that determine shapes of fields. But if you've got unusual field shapes, you might have more edge, so that if you're sampling near the edge, you might get much more unusual results than you would near the middle. Right, which I just explained. This is something else that as I progress through the class and get better at teaching it, I'll remove all these silly animations that I click through later. So there we go. Again, part of the process. All right, so how do we increase precision? One thing that we should point out right off the bat is that low precision, as we mentioned before, is in and of itself not a huge problem. You can basically get over precision as long as precision is focused around an accurate population estimate. And so as you're basically fine with low precision as long as that precision doesn't skew your accuracy. If for whatever reason most of the precision points are starting to skew a little bit away from the center, then you've got a problem. So the easiest way to increase precision is to increase the number of samples you take, right? So if you're starting to skew a little bit, you can sample more often. It'll give you greater confidence that you are near the true average of the population. One challenge with this, of course, is that monitoring and sampling is not necessarily expensive, but it does cost money. It costs money in terms of having to pay someone to actually go out and do it. If you're running lab analyses, you have to pay someone in the lab to run every single sample you send. But it's also expensive in time. Basically, any field that you have to spend more time monitoring or sampling is a field that you're not sampling somewhere else, a potential client, or potential work that you could be doing on something other than sampling. So basically, the general rule is that if you're unfamiliar with the pest, if you're unfamiliar with the system, it's good to err on the side of safety. Do a little bit more sampling than you think you need to, and then as you get more familiar, you can sort of push things down and find a nice sort of ideal place that you can sample at. And then finally, one way to increase precision is to account for that pest distribution we talked about earlier. If you know that the species is going to clump, try and set up sampling techniques that account for clumping, right? So basically, yeah, cater it to the species you're looking for. And as we went through in lab last week, the nice thing is that oftentimes, if you're familiar with the pest, or if you're unfamiliar with the pest, the UC has a lot of sort of background information on what you can expect to find in the field. All right, what time we got? Oh, 1:15. We got time for a little more. All right. So, one tricky thing with sampling that you need to consider is the reality of sampling efficiency, which kind of touches on what I mentioned on the last slide. The idea that sampling does cost money, whether that's an expense of time or an expense of money. And as such, ideally what you want is you want to have a sample that's large enough to give you an accurate estimate of what's in the field, but is small enough that it doesn't cost you a ton of time or a ton of money to get that estimate. You want to find that nice middle ground. And when we talk about this middle ground, we use the term sampling efficiency, or the ratio between the total cost and the accuracy of a sampling technique. So if I were to say that a technique is very efficient, that means that it sits nicely in that sort of middle there. You have kind of like a nice 1-to-1 ratio of accuracy to sampling technique, where we're basically not sampling too few, we're also not sampling too many. So basically we're sitting at a nice sampling optimum. The appropriate number of samples, well, I got ahead of myself. So sampling optimums. So oftentimes finding that sampling optimum is a little tricky if you're trying to do it yourself. The nice thing is, as I mentioned before, there's a lot of people who have done research on this, and so they can give you a guideline with where to start, and then you can sort of manipulate those guidelines as you see fit to work with whatever system you're in. So, if they're saying treat when you find 5 weevils, per sweep, you could start there, but then if you decide, I think I could push that up to 6 or 7, and we'd still be okay, because insecticide is cheap right now, then yeah, there's no reason not to manipulate it a little bit. All right. Let's start. Let's get through this. Let's try and get as much done as we can. So, there are lots of ways that we can try and work around sampling efficiency in order to create sampling techniques that are as efficient as possible. One of which is a trigger. So basically a trigger is a biological or a physical event that's directly related to the pest development, and we use that to trigger the actual sampling, right? So if we need to go out and say sample stink bugs in tomatoes, we could either go out and we could turn over leaves and we could look at the fruits every single time we go out there, which is pretty intensive. You have to walk through the field, you have to turn over a lot of things, you have to get on your hands and knees. Or we could use a pheromone trap. So you could use a stink bug traps are fairly easy. It's sort of like a gallon jug that you can cut the side out of and put the chemical in the bottom. If you don't think there are any stink bugs yet, you can set out your pheromone traps. Every week you go out, you look in your pheromone traps, see if there are stink bugs or not. And if there are no stink bugs, there's no reason to go out and look at the rest of the field, right? But as soon as you see those stink bugs, that's the trigger. That means, all right, we've got stink bugs in the trap. It's time that we actually start looking in the field to see if there are enough of them that are causing damage. Another nice technique would be something like presence-absence sampling. So presence-absence sampling is really nice. It's kind of like what we did with the spur samples. You don't need to go out and count every single pest that's in a unit, right? You don't need to check and see how many San Jose spurs there are on a spur. You just need to know whether they are there or not. And that can save you a lot of time if you're dealing with something like spider mites that are really, really tiny and take a long time to count. But it's nice if the monitoring guideline is just go out and count the amount of webbing that you find, right? Go to a tree, estimate the number of webbed over leaves, and then that's a nice, easy presence-absence sort of test. There's also sequential sampling. And we'll wrap up after this one. So sequential sampling is what we did with the spurs, right? The idea being that you gather, when you go out and you gather the samples, you gather more samples than you actually need. You check a subset of those units that you have collected, and if they are above a certain threshold, you treat. If they are below that threshold, you don't treat. But if you're somewhere in between, and it's hard to tell if you are at threshold or are way below it, you count another subset, right? And so essentially, in the spurs, we counted 20. If we were above a certain number of scales, we treated. If we were below, we stopped counting. But if we were right in between those two counts, we moved on to the next set of 20. And this way, in the vast majority of cases where you have very low populations, you only have to count 20. In very high populations, you only have to count 20. But you only have to count a lot when you're in that in-between area where it's harder to make a decision. And so basically, you're just reducing the total number that you need. And it concentrates the sampling effort only when it is absolutely needed. All right, so with that, I just had an example, but we've already gone through this, so you've seen the way that those sampling cards work. But so that's sequential sampling. With that, we'll leave off. It looks like we have a handful of slides that we'll get to 1 week from today. So, I'll see you in lab, or I'll see you next Thursday. Either way, I hope you make it to the World Ag Expo. It's pretty cool.
Just